We present a novel control architecture that allows legged robots to dynamically traverse complex terrain. At its core, this is a layered architecture that separates out the choice of discrete variables from a smooth optimization. Once the discrete variables relating to the hybrid nature of the system have been fixed, the resulting optimal control problem is a classical nonlinear program that can be solved efficiently with gradient-based methods. First, terrain contacts are sampled, as shown here. Then these samples are fixed in the smooth MPC. The MPC trajectories and forces are visualized here. The MPC is parallelized to evaluate all the context samples at once, always applying control from the lowest cost option. These controls are then sent to the robot. The controller is ultimately using a combination of gradient-free and gradient-based optimization to solve the hybrid optimal control problem. This blend of numerical techniques allows for real-time control. In fact, it is fast enough for real-time control of a humanoid robot as we demonstrate here in an asynchronous simulation. 25 degrees of freedom are being optimized at 100 Hz. To choose terrain samples, a random number is sampled between 0 and 1. Each piece of terrain within the kinematic limits of the robot is associated with an interval between 0 and 1 and weighted by its area within the kinematic limits. To prevent resampling the same terrain combinations, a tree structure is used to keep track of the available combinations. Polytope constraints are then extracted from the sample terrain and enforced in the MPC during stance phases. Only 2 to 4 samples are generally needed for this task. The robot is able to traverse over a variety of terrains and can still locomote efficiently on flat ground. We can compare the sampling-based method for selecting terrain to a common heuristic approach, and we see that the sampling-based method is both more optimal and more reliable.